Okay, so now we're going to talk a little bit about empirical formula and molecular formulas and how to determine them. So an empirical formula, just so you know, is the simplest formula, is a whole number ratio of atoms present in a compound, okay, and the smallest ratio. Whereas a molecular formula, okay, is the true formula. It tells you exactly how many atoms of each element are in that molecule. Now, they can be the same, but they're not necessarily the same. Empirical formulas do not have to be true molecules. So let's take a look at a couple of examples. So I'm going to have on the left-hand column the empirical formula. On the right-hand column, I'll have a molecular formula. Okay. So the first substance we're going to look at is water. And if we look at water, the molecular formula is H2O, but that's also the empirical formula. That's the simplest ratio that's in this molecule. What happens if I look at something different? Suppose I look at hydrogen peroxide. We know hydrogen peroxide is H2O2. That's the molecular formula. But the simplest ratio is HO. This is not a compound, it's not an ion, it just tells me that for every oxygen in hydrogen peroxide, I have a hydrogen. That's the simplest ratio for empirical formula. Now there are several molecules that can have the same empirical formula, but different molecular formula. So if I gave an empirical formula of CH, there's a compound, acetylene, that's C2H2. That has this empirical formula. Another compound, molecule that has this formula is benzene, which is C6H6. Okay, so molecular formulas, what that means is in water, I have exactly 2 hydrogens, 1 oxygen. Hydrogen peroxide, I have exactly 2 hydrogens, 2 oxygen. Empirical formula gives me the simplest ratio. Okay. So while this can be a molecule, these are not. Now it turns out to go from empirical formula to molecular formula, look at it, I need 6 CH units to go from CH to C6H6. And from here, I need 2 CH units. So one of the aspects of why we're so busy looking at empirical formula is that that's my smallest little group that I need to make my molecule. The one thing is we do not write it like we write ionic compounds. Remember, it's a molecular formula, so this is a molecular compound. So you don't use parentheses, you just multiply the number of units into your subscript. So this uses 2 OH units. Okay, you could just say this is 1-to-1, so you just need 1 H2O unit. So, that's the difference between empirical formula and molecular formula. Now let's take a look. How do we determine empirical formula? So, I'm going to write down the set of rules to follow, and you'll want to do the same. Just follow the rules. Okay? And what you're going to do is, if you start off with mass percent composition, because that's what we had just been calculating. So when you have 1 mass percent composition, okay, then what you're going to do is you're going to assume you have exactly 100 grams of your sample. Okay, when you make that assumption, if you're not given your masses but given mass percent, then what this means is that you can convert your mass percent composition to mass in grams. Okay, now since we're talking about composition, all of the percentages will be for elements. So now that we have our masses, 3, you're going to convert your mass of each element to moles. Alright? And after you do this, you're going to divide by the smallest number. So whichever moles is the smallest number, you're going to divide by that. So you're going to divide by the smallest value you obtained at 3. Okay, and then 5. And this is only if necessary. If necessary, you can multiply all your subscripts to remove fractions. Okay, so let's take a look and see if we can give you an example, and then we'll get an example for 5 so that you know which of the fractions you need to be focused on. Okay, so let's try this one. Okay, so and keep in mind the rules, and I'll go through them as we do. Suppose you have a sample with composition of 56.58% potassium, 8.68% carbon, and 34.73% oxygen. Okay, so determine the empirical formula. Okay, so step 1 is if we assume exactly 100 grams of sample, then when we convert our percents to masses, these numbers don't change. So 56.58% of 100 is 56.58 grams of potassium. Okay? This 8.68% of 100, that means it's 8.68 grams of carbon. And 34.73% oxygen is 34.73 grams of oxygen. So that's all you have to do. So when we assume 100 grams of sample, then our percentages just become our masses. So we finished step 1, assuming it. Step 2, we convert to masses. Step 3 was to convert mass to moles. Okay? So when we convert mass to moles, then what we're going to do is use, again, our periodic table. So have your periodic table always handy with you now, because we're going to be using it and relying on it very heavily. So potassium, okay, has a molar mass, let me look it up, 39.0893 983 grams for every 1 mole of potassium. Okay. Carbon is 12.011 grams of carbon for every 1 mole of carbon. Oxygen, we said, was 15.9994 grams of oxygen for every 1 mole of oxygen. So now all we're going to do is convert our mass to moles. And what we get, 56.58 divided by 39.0983. Get a 1.447 moles of potassium. 8.68 divided by 12.011. I get a 0.723 moles of carbon. And then 34.73 divided by 15.9994. I get 2.171 moles of oxygen. Okay. Now, we have to divide these by the smallest number. So, of these, 1.447, 0.723, and 2.171, which is the smallest number? It's going to be the 0.723. So we're going to divide every single value that we obtained by the 0.723. Okay, so I'm going to erase this part, move to the left. When we do that, for potassium, the 1.447 divided by 0.723, I get 2.00. Okay? For carbon, it's divided by itself, I get 1. And for the oxygen, I get 3.00. So these are basically all integers. You want these to be integers. So potassium 2, 1 carbon, and oxygen 3. So this is our empirical formula. Okay, so let's try one more example in the next slide.